Good afternoon, everyone, and thanks for joining us. I hope the conference has been great so far. My name is Paola Lorusso. I'm a manager of a great team of database specialist solutions architect. And we support our customers every day in their cloud journey with our experience in database domain. And today, I have the pleasure to have with me two of our customers, Vijay, Principal Engineer at Twilio, and Sid Clay, Distinguished Engineer at ADP. Today we are going to discuss about stories of evolution, the evolution of application architectures that evolved over time, the application requirements that have changed over the years, and how the organizations are taking advantages of a purpose-built database approach to build modern applications. We will start with why choose a purpose-built database approach and how it is important for everyone. It can help everyone like you to build modern applications. And we will see this in action with Twilio and ADP cases and how they were able to unlock the value of their data with a modern data strategy. I want to start with one of the most fundamental questions that I get from our customers. Why a purpose-built database approach? And if you have this question in mind, you are in the right session. When I meet customers like you, they start describing their main application characteristics. They have a monolithic application. They want to modernize this application. They are experiencing a data growth, and they want to use this data for their business. But at the same time, they are not really flexible in scaling their database environments. So I want to answer this question today, why a purpose-built database approach, and why it's so strategic for every organization, for you, to be more agile, more competitive with their data, with your data. We have seen an evolution over the last decades. We can say an evolution of application architectures. Back to 60s, 70s, mainframe was the predominant way to build applications. And then we have seen client-server applications. And when internet arrived in 90s, we have seen three-tier applications. We have seen an evolution because all these, in these architectures, it became more and more distributed in nature, with the client and the application code more distributed, but always running against a single database, a single relational monolithic structured database. What has changed? With the cloud, in the cloud era, the organizations are taking advantage of a huge wave of innovation technologies. And we can say that the cloud has really changed the way we do business because of the cost of the compute and the storage has come way down. And now the organization, you can store more and more data, more than ever before. And microservices is the way that applications are built in the cloud today. We have seen another evolution. The expectations of application developers and the end users of today's applications has changed. It's very different from what is used to be. Now in the digital transformation, the organization wants to build modern applications. They want to build internet scale applications. They want to serve millions of users. They need to store exabyte data. And they want to have applications that are globally available. They want infrastructure that can perform at a single-digit millisecond when there is a traffic fluctuation. And there is also another important aspect, an economic aspect. Organizations like you can use pay-as-you-go model pricing. And with this, you pay only for what you use. And this is an important evolution because you can experiment more, you can fail in order to innovate. And we will see today how AWS can help you, can help any organization in building modern applications. And we will see this in action with Twilio and ADP. But how is this connected with another important evolution, the adoption of a purpose-built database approach? When customers make a shift from monolithic to microservices applications, they are effectively able to accelerate the development of their applications. They start, in fact, with their monolithic applications where all the components are tightly coupled, and they are able to split these monolithic applications into services in pieces that are independent pieces. An important aspect here is that each single component is designed for a specific purpose, is designed to satisfy specific application requirements. And these components are loosely coupled. That means, for example, if a service goes down for any kind of reasons, this doesn't impact the rest of the ecosystem and other services. They are independently deployable. That means effectively that the teams, each teams, can work in parallel in multiple applications in the development of different services at the same time. And they can scale independently. That means, for example, if I need to add more resources, CPU capacity or memory to a specific service to satisfy specific applications requirements or workloads, this could be possible, and it is reserved to a specific service. And we have said that each component, each service is designed for a specific purpose. They need specialized resources to satisfy their application requirements. And in this case, it means that developers who build with a microservices approach in mind want to use the right solutions for their applications so that they have never trade-off between functionality, scalability, high availability, security, and performance. They know they need to manage a variety of access patterns, different data types, and different workloads. So they want to have the right database for their specific application requirements. So it means they want to use the right tool for their job. Because in this case, they cannot use one single database that can satisfy all the possible access patterns. And AWS provides the broadest portfolio of purpose-built databases. With our experience in managing infrastructure for Amazon.com, we realized that relational databases were good for relational workloads. We're still good databases. But at the same time, we had scaling issues. And this triggered us to build and reimagine these relational databases, all guard relational databases, into the cloud with Amazon Aurora and Amazon RDS. And the advantages is for sure to use engines that we knew, but also the elasticity, the high availability, and the durability of managed services. And for other cases, use cases where probably a NoSQL database was a perfect choice, we designed a specific service. For example, for key value workloads, we designed and introduced Amazon DynamoDB, our fully managed NoSQL database that provides consistent single-digit millisecond latency at any scale. And for graph workload, we introduced Amazon Neptune. And for other cases, for example, managing a JSON document, we introduced Amazon DocumentDB. And with this approach, we identified every time a specific use case with unmet needs for workload characteristics, for different access patterns, and we introduced a specific database service. What is the advantage of this? So every organization, you can choose exactly the right tool for your job. Every organization now can really unlock the value of their data. They can find insights in any data type and make this data available to everyone. Now, let's see this in action. So we will see with Twilio and ADP how they were able to use this approach to build modern applications. Thank you, Vijay. Over to you.
Thank you, Paula. Well, welcome, everyone. Thank you for joining us here today. My name is Vijay Bhatt. I'm Principal Engineer at Twilio, and I'm excited to share with you my team's data modernization journey. So first, let's answer the question, what is Twilio? For those who are not familiar, so Twilio, we are a leading customer engagement platform. So we help you as a business to build direct, personalized relationships with your customers. For example, let's say you book a ride on Uber or Lyft, and you get that text message saying that a ride will be here in 5 minutes. That's an example of Twilio in action. Now, how do we do this? So we built a global enterprise scale communication platform, a communication platform as a service. So to get a sense of the scale, we send over 144 billion messages a year, process 54 billion voice minutes, 1.5 trillion emails, and we do this by working with over 1,500 carriers in 180 countries. And we allow you to reach your customer no matter where they are in the globe. On top of that, working across all these countries, we make sure that you are compliant with all the rules and regulations that you need to follow when you operate in that country. We do all the heavy lifting for you. So that's the communication platform. But on top of that, we also help you really understand your customer. So we help you pull together various data sources that you have of your customer, all the touch points that you have with your customer, into a data platform segment. And that allows you to build a single user profile of your customer to really understand them. And this can be used for many use cases. For example, Twilio Engage, which is our marketing platform, allows you to reach the customer at the right time, the right channel, with the right message to delight them. So this is what we do at Twilio. Now let's pop the hood and see what happens when you actually send a message using Twilio. So let's say you're a developer. You integrate with Twilio's SDK, and you call the API to send a message. So that gets into the API gateway. And for simplicity, I have called all the services that orchestrate the sending of a message under control plane queuing services. So what's happening over there is a very complex mechanism to manage throughput of messages as they flow across different providers and different networks to make sure that they reach your customer on time with the service guarantees that you expect from us. So that's in the control plane. However, we also want to be able to track the state of the message, the metadata, as it flows through the system. And this happens in another service called in-flight. So all the messages are in flight. We store all the metadata about it, and it's used for sending and receiving messages. All that data flows through Kafka and is put in a historical data store called post-flight, which is going to be the subject of our conversation today. So post-flight is a service that stores message metadata, the message logs, in the long term, and allows you as a customer to be able to access them through the API, which I have shown here as the data plane services. So let's dig into what messaging post-flight is responsible for, because that will inform our technology choices for how we want to modernize the system. So messaging post-flight, as I mentioned, is responsible for long-term storage and retrieval of message logs. You can do this by querying a single message ID or by applying various filter criteria, such as what messages did I send with a particular phone number and on a specific date. So you can do these kinds of queries to understand how you have interacted with the platform, and you can use it for a variety of use cases, such as analytics, if you're trying to build a call center, a customer service center, and so on and so forth. On top of that, we store a lot of sensitive data in the message logs. For example, the message body can contain PII data, and we take that control of that data very seriously. So we offer a variety of privacy controls, such as message redaction that allows you to redact the body and the phone number, the PII data from the message logs. And also, we allow you to set custom data retention policies. So by doing that, you can say that data is only going to reside on Twilio servers for a set amount of time, after which it gets deleted. So you have full control of your data. Now let's dig into what the technology that used to drive messaging post-flight. So messaging post-flight was an API layer that's built on MySQL cluster. So it was a sharded MySQL cluster sharded by account ID. So what does that mean? So based on the range of account IDs, all the data for those accounts will reside in a particular shard. And each shard comprises of a primary node, three read replicas, and an analytics node. So each of these nodes is an EC2 instance that's running a MySQL server. And we had 20 of these shards at the time of migration over to DynamoDB, which I will talk about in a minute. So that's 20 times 5, 100 machines that we need to manage manually. So as you can imagine, this was quite a complex task. In terms of what kind of traffic we used to see on the system, so we see a peak load of about 620 million messages a day. And we store about 260 terabytes of historical data. We have a very write-heavy system, and the reason for that is that any message that flows through the system necessarily needs to write metadata into the data store, but the reads are only determined based on what queries customers apply against the API. So we had roughly a factor of 4 difference in terms of reads versus writes. So based on the legacy architecture, there are a bunch of challenges that we need to face. One of them, the most common one, was the noisy neighbor issue. So we have certain large customers who send bursts of messages for certain campaigns, and this would create a lot of write pressure on the MySQL nodes, on that particular shard. And by doing that, what would happen is that it would impact performance for all other accounts in that particular shard. In fact, sometimes traffic would be so high that because of a lot of threads being open on the primary node, it would be briefly unresponsive, and that would cause quality issues for the end customer. And this would require a lot of manual intervention by the on-call engineer to throttle processing speed, and that would create a bunch of data delays down the line. And this was a bad customer experience. So this is what would create a bunch of maintenance complexity to keep the system online and running. Now the question is, okay, we have a sharded system, so can we just not split it up into more number of shards and kind of reduce the burden on any individual shard? That's a great question. We had been doing that for a long period of time, and we got to the point where we couldn't do it anymore. We had actually run out of room to be able to split it any further. So we're at a crossroads where we had to decide how to make this simpler to scale. So on top of having a system that was sized for peak load, you can see that when there's not as much traffic flowing through the system, you still have a significant amount of unused capacity. And that's dollars that's just getting wasted, right? So we wanted to find a better solution. So we explored a variety of different possible solutions, and Amazon DynamoDB was a really attractive candidate. The primary issue, the reason why it was very attractive is because the data access patterns that Postflight needed to serve all the API requests was very compatible with what DynamoDB can provide. So single message lookups and range lookups by key range that perfectly fit in with our use case. So that was number one. Number two is that it's a fully managed service, serverless. So we don't have to care about sizing or provisioning or knowing what kind of machine type to provision for, and so on and so forth. So that made it much simpler. And as Paula mentioned, all the requests to DynamoDB are very low latency, high throughput in nature. So we're able to service the same API requests to our end users without any degradation in quality of service. We have virtually unlimited storage. We don't need to size any servers. And also, the other thing that's really cool is the auto-scaling capacity. We can scale reads and writes independent of each other. And as long as we get the schema designed correctly, we can scale virtually infinitely. So these were very attractive reasons for which we chose DynamoDB. So I want to get into what the final solution actually looked like. So as you can see over here, there are a few more boxes in this puzzle. There was a larger org-wide effort to build a messaging data platform. It was a single source of truth for messaging data. And the post-flight migration was part of that story. So there are a few things that we built out here. So as you can see, DynamoDB is taking the place of MySQL. And there, we made sure that we designed the partition key correctly to prevent any kind of hotspotting, because that was an issue for us with large customer accounts sending a lot of traffic. So we wanted to make sure that that design was nailed down. And then the other part, as you can see over here, is so there's a history search service and a history search API. That is taking place of what used to be post-flight before. So what's going on over there is we're splitting out the ingestion from the API servicing. So that way you can scale those independent of each other. So these are a few things that went in there. There's a lot more complexity in the solution, but at a high level, this is what's going on. Another piece to call out over here is the analytics portion of it, which is another component of the messaging data platform. Previously, you could run analytics queries against the analytics node of the MySQL cluster, which, as you can imagine, is you don't really want to be running queries against a user-facing data store. So this way, by separating out the analytics portion into an entirely different system, you can run Spark workloads on it, which is more in tune with what you would need to do for running analytics type of applications. So this is what the solution looked like. I want to go over what the results were of doing this migration. So one of the main problems that we had with the old system was we used to have frequent data processing delay incidents. So whenever we'd have these, there'd be multiple hours over which there'd be delays for customers to be able to view their message log data. And this would cause, it was not the best in terms of promoting customer trust. After we completed our migration, from 1 per month, we went to 0. We did not have any more of these delays. Another thing to call out is Black Friday, Cyber Monday, BFCM. So Black Friday, Cyber Monday are banner days, our biggest data processing days. That's when we get our peak traffic. In 2020, we had 2 big delays of 10 hours and 19 hours. And in 2021, we had 0 delays. So that was like an astounding change. And I have to say, I'm very proud of the results that we were able to achieve. And on top of that, we were able to save on infrastructure costs by retiring the legacy MySQL cluster that was scaled for peak capacity. We were able to save over $2.5 million in annualized savings. Something that I want to show you from just a few days ago from Black Friday this year. So this is illustrating how you can use DynamoDB auto-scaling to make sure that you have exactly the right amount of capacity for the time when you need it. So the purple line up top is the provision capacity for DynamoDB, the write capacity. And the blue line underneath it is how much of that capacity is actually being used. So by enabling auto-scaling, you can make sure that you're paying for just the right amount of capacity that you need at that point in time. So you're using resources very, very, very efficiently. And on Black Friday, we actually scaled up by a factor of 9, which is amazing. We would not have been able to do this with MySQL at all. So this is fantastic. So I want to go over a few key things that helped us achieve this goal. So one of them was really, really, really understanding our current workload and really monitoring it and understanding what's going on under the hood. So this is a legacy system. A lot of our team members were new, not very familiar. So it's key to really instrument as much as possible and understand the data access patterns. So that was really helped us identify whether DynamoDB would be a good solution or not. The second one, the proxy approach. This is kind of a trick or an industry standard approach to be able to effect a migration in a zero downtime manner. This is the proverbial changing the tires where the car is running. So the way you do it is you stand up a proxy in front of your legacy system. You build your new system, and then you can split the traffic between 2 systems depending on how mature it is. So when you're starting off, when you stand up your new system, you're operating in shadow mode. So it's only sending data back to the proxy, you can compare results, and you gain confidence, and you know that the new system is working well. And as you gain confidence and you fix the bugs, you can start sending some of that traffic back to the customer until you migrate all traffic from your legacy system to your new system. So that really helped us catch a lot of issues without customers even noticing. So I think that really helped us out. Number 3 is data validation. So when you're migrating data from two extremely different data stores like MySQL and DynamoDB, you really want to make sure that the data in the old system and the new system are at parity. Otherwise, customers will notice. So we spent a lot of time and effort trying to get this right. As you can imagine, with 260 terabytes of data, doing a data parity between two systems would have been very time-consuming and very expensive. So what we came up with was a partitioning and sampling approach. That way, we partition the data by date, migrate the data, do a sampling approach to validate that the data is correct, and with a certain statistical guarantee, we can say that the data is exactly the same between the two systems, between the two partitions in the two systems. And that way, we're able to do the entire migration and know that the data is at parity. Another one that I want to tell you about that really helped us out was our partnership with AWS Professional Services. Like, they really helped us through this journey, really to bounce ideas and to also understand if our approach would work. And the most key thing for us was they helped us identify and also come up with a novel solution to this partition hotspotting problem. Since we have such a write-heavy system with a lot of large customers with large volumes of writes, we wanted to make sure that write hotspotting would not be an issue. So we prototyped a POC where there was a novel synthetic partitioning approach to be able to spread the writes across multiple partitions that were able to demonstrate that even with a much larger write volume than we're seeing in production, we would not hit any write hotspots. So this partnership was really valuable for us. So if you have the opportunity to do so, I would really encourage you to reach out and work with AWS Professional Services. It really helped us out and really helped us with our journey. So that's it from my side. I'm going to hand it over to Sikli so he can share his ADP story with you.
Great job, Vijay. Hello, my name is Sikli Suarez. I'm a distinguished engineer at ADP. And today, I'm going to be sharing some highlights with you about our product modernization journey into the public cloud. Hopefully, you're going to leave this presentation today with better understanding about ADP product offerings and our lessons learned while choosing our databases to build our applications. Most of you may know ADP as a payroll company. Yes, we are the global leader on payroll and human capital management solutions. Recently, we achieved a big milestone. More than 1 million companies trust ADP on their business. ADP pays globally 39 million people, 25 million people in the US, and 14 million people outside. We pay 1 in 6 people in America. And we move annually $3.1 trillion paying these employees. Our ADP mobile solution receives 2.8 billion logins annually. Data is not only part of our name, but it's part of our core business. When it comes to companies ranging from dozens up to several thousand employees, ADP has 2 human capital management solutions. ADP Workforce Now, targeting mid-sized companies in North America, and ADP NextGen HCM, which is our global human capital management solution. ADP NextGen HCM already federates into 9 countries in Americas, Europe, and Asia Pacific. Regardless of the HCM choice, both systems share the same ADP ecosystem. Today, I'm going to be presenting to you more highlights on ADP Mobile and Next-Gen Payroll. All these solutions are deployed natively on the public cloud and are backed by AWS. So the first system I'm going to be sharing with you here today is ADP Mobile. ADP Mobile started development in 2011 in our on-prem data centers, and recently we started our migration journey into AWS. As I was mentioning before, ADP Mobile receives 2.8 billion logins a year. In our application, we receive 15.5 million unique users and almost 280 million monthly visits on the application. ADP Mobile is our front gate when it comes to employees and managers using ADP products. People come here to see their paychecks, enroll in benefits, punch in and out on-time systems, and among other things. When we started building ADP Mobile, we had a challenge. As I was mentioning to you, ADP Mobile is our front gate for many different products inside ADP. We wanted to reduce the amount of orchestration in order to render front ends. Every time we have to render front end, we need to traverse different SORs inside ADP. We wanted to consolidate the data as much as we can from these different systems so it would be easy for us to render, again, the front ends on the mobile side. And finally, we wanted to simplify the way that the systems need to traverse into the system, into the ADP mobile system. The solution I'm going to present to you here is started on our data centers. So the technologies that you see here on the cloud were very similar on our on-prem. Instead of SQS SNS, we had Kafka. Instead of Lambdas, we had Docker containers on top of Docker Swarm. And instead of Neptune, we are using a proprietary graph database solution. But the flows are the same. So in ADP ecosystems, what you see on the top right side is anytime there is changes on our ADP ecosystem, today we already send messages to notify other domains inside ADP that changes are happening. When we created our AWS solution, we exposed new endpoints in AWS API Gateway, and we started listening to these events that comes from these different SORs. There are two types of events that mostly happen inside ADP: batches and drips. Batches are a group of changes that are happening for several employees on the same organization. Think about people changing department from department A to department B. A drip is a change that affects a single person. Think about an event like being new hire or promotion. When we receive batches, what you see here is FlexGraph Producer receives that message from SNS SQS, break that in chunks, sends it back to SQS SNS. Then FlexGraph Consumer consumes the message as a drip, changes that, transforms that into a graph representation, and stores that in Neptune. Later, when we have access that comes from ADP Mobile, we can now go straight to an API in AWS API Gateway, serve this request through FlexGraph API, and go straight to Neptune. In our journey to move our application from our on-prem data center into the cloud, we had to go through many, many steps. We wanted to move into managed service and remove as much toil as possible in this journey. The first thing that we had to do is our graph database at that point in time that we had on-prem was only compatible with Cypher, which at that point in time, Neptune was not compatible with. So we decided to move to Gremlin as a GraphQL language that would be compatible with both on-prem and in AWS Cloud. So we migrated to Gremlin, and then the code started to be compatible with both clouds. One thing to keep in mind here is that our use cases for Neptune are very write-intensive, and Neptune scales vertically. So you need to make sure you size your instances and make sure you're going to handle the throughput you have for your write operations. Another thing that you need to keep in mind is that read replicas and write replicas need to be the same size and type, so in case you have failover situations from the read replica becoming write replica, we don't get into situations where you can now handle less throughput. What were the results that we experienced moving our workloads into the cloud? First of all, our performance just moving from that on-prem database into the cloud became 10 times faster processing drips. We used to process a drip around 100 milliseconds, and when we migrated to Neptune, we started seeing 10 millisecond average processing drips. The second thing that this helped us is speed to market. Now we can move way faster use cases, especially read-only use case in mobile, because now we don't require anymore going to different domain systems inside ADP and asking them to provide new APIs. I can go straight to my database now and provide those use cases. Last point I want to make here is that serverless dramatically reduced our cost. I can't get much into the details here, but just to share just one idea with you, what we used to spend just in licenses on our on-prem graph database clusters was more expensive than what we spend today in all environments we run Neptune, from development to production. The next use case I want to present to you here is ADP Next-Gen Payroll. This is our global platform for run payroll applications. Next-Gen Payroll already supports more than 3,000 clients in 6 countries. It's a global first approach to developing a payroll platform. Before, ADP used to have payroll applications in each country that we support clients. And each of these applications that we have payroll is a different code base with a different development group. Now we are moving to a policy-driven approach to develop the payroll platform. Instead of having different code base and different development teams, it's the same development team that develops a global platform. What we have now is center of excellence, where we have clients, and in this center of excellence, we have subject matter experts, payroll specialists that translate in-country payroll rules into policies that are then deployed on our platform. With that, we are building transparency. How many of you here understands in details or can tell the details about your paycheck? How many of you can easily understand why your paycheck, this pay period, is different than the previous pay period? It's tough, right? There are many reasons why your net income in a paycheck can be different. You may have maxed out your 401k contributions. You may have maxed out your social security contributions. In those use cases, your net income will be higher. But most likely, your taxation will also be higher. We want to make it extremely easy for employees to understand how they're getting paid. This next diagram here shows a flow in our payroll solutions. Normally, in order for a payroll to run, a payroll practitioner logs into our HCM systems, and they go into a payroll dashboard where they see all the employees that are about to get paid. On that screen, they can do adjustments, they can change rates, they can fix hours, and understand which employees will be executed. There are two main flows in payroll, a payroll preview and an approval process that triggers downstream integrations. I'm going to explain both in high level to you here. So once this payroll practitioner goes into that payroll dashboard, they normally start a payroll execution. For that payroll practitioner, this is a single transaction that affects the whole company. When we receive these calls in our EKS clusters, we break that down on a per employee basis. Our payroll today runs is employee-driven calculations. So for each employee that we have, we receive the call on our side, and we go back to Amazon Aurora MySQL to collect their year-to-date earnings, which is the year-to-date data for deductions and earnings that you had so far in this year. Then we grab hours and rates, we calculate a new payroll, and we store that in Aurora again, and also in Elasticache for easy access, high throughput. This information then goes back to the practitioner. They can now verify if everything is correct, and now they start an approval process on that payroll. This would then trigger downstream integrations. Using USA as an example, downstream integrations will be things like generating paychecks and storing that in S3. Starting money movement processes that would go to employer's account and move money into the employee's account. Generate W2s, withhold taxes, etc. Would be really hard for me to explain all the details on the payrolls, but these are the main two flows we have in payroll transactions. So why we chose Amazon Aurora MySQL? Actually, when we started this project, we went to our extreme GA requirements, which is we need to run payroll for millions of employees. And we started on the extreme opposite. We started with no SQL databases. The first database that we used was Cassandra. And for several months, we were running our systems in Cassandra, but at some point, we start finding consistency issues. Then we moved to Apache Ignite, which was our second choice. But again, facing consistency issues. Then we went to the basics. Payroll is essentially a transactional OLTP system. So we decided to move into an open source relational engine. And we chose MySQL because it was one of the most, if not the most, relational database engine. And then we started our journey of using MySQL that started in 3 waves. First, we started running our own MySQL clusters on top of EC2 instances. Then we moved to RDS. And finally, we moved into Aurora MySQL. Again, the goal here was very similar. We want to move as many services to managed service as possible. So what were the business benefits for us? Well, it would be very hard for me to tell you that our performance is way faster than our current gen systems. Our current gen systems are really good. Actually, in some cases, computing and storage runs on the same big box. What I can tell you for sure is that we are able to now move resources to do what ADP does best. And what we do best is creating the best payroll and HCM solutions. ADP is a 60,000 employee company size, and we have more than 10,000 employees in technology. But if you'd ask any leader, any technology leader inside ADP, they would tell you they need more resources because we need to build more. Amazon helped us focus technology people that were focusing on running clusters, Kafka clusters, database clusters, to now focusing on building our core business. Another thing that Amazon helped us is region segregation for compliance. Think about GDPR rules that we have in Europe, or GDPR-like rules that we have in New Zealand, Argentina, or Brazil. Now, instead of running our own data centers on those regions, we can rely on AWS to run our payroll platform on those regions and making sure that the client data is isolated on those countries. The next point here is that our global policy platform really is helping our multinational companies understand better their payroll across the globe. Things like pension plan, for instance, where in the US it's called 401k, and in Australia it's called superannuation, would be very hard to compare in an ecosystem where you have a different code base in US versus a different code base, a different development team in Australia. Now all these clients are being implemented on top of the same platform using the same policy constructs. It's much easier for these multinational companies now compare how much employees are spending in pension plans in US versus Australia. This platform also makes it possible for companies to do benchmarking. Even though the constructs for payroll is different on a per company basis, they are still relying on the same structures. What are the technical benefits or Aurora benefits of moving to MySQL? First of all, Aurora MySQL is 100% compatible with MySQL, and that was great in our journey. But besides that, we also got a automated failover engine and 6 copies free, corruption-free of our data. We also get point-in-time recovery up to 5 minutes and daily snapshots up to 35 days. For us, it became a very cost-effective solution for development environments. In Action Payroll, in all development environments, we use Aurora MySQL serverless. So we are able to scale our applications in our databases when we are using them and shrink it back to almost 0, or in some use cases, even 0 when we are not using these clusters. The last point I want to make it here before I switch this back to Paola is that Aurora MySQL became very easy for us to do prototyping. Before, prototyping things on data centers would mean sometimes that you need to pay upfront cost of buying licenses or hardware to make sure your solution is going to work in your on-prem data centers. Now we can easily go to AWS, instantiate database instances, try it out, POC, and if this works, great, move to production. If it doesn't, destroy, stop paying, you're good. AWS provides us a very big undo button, and that's great. Thank you.
Thank you, Vijay, and thank you, Sid Clay, for sharing your use cases. Absolutely. We have seen that data explosion requires the organization to adopt a modern data strategy. And data-driven organizations such as Twilio and ADP have really understood the power of data. They really treat data as a strategic asset for the organization. And not just to use this asset for big decisions, but for everyday actions. And they have understood that, for example, for really be empowered by data and get the most from their data, they need to build modern applications. They are really able to work with any type of workloads. They can really use any kind of data types and implement any access patterns. So the developers who need to build with this approach in mind, microservices approach in mind, want to use the right tool, the right service, database services for their specific unique application requirements. And AWS provides the broadest portfolio of purpose-built databases so that developers have never trade-off functionality, scalability, high availability, performance, and security. And with that, we have been very glad to have you here. Thank you again, Sid, Clay, and Vijay, for sharing your use cases and really to help us understand the power of the data. How it is important to be a data-driven organization and modernize with AWS purpose-built database portfolio. We will stick around for any questions. Thank you, everyone. Enjoy the rest of the conference and get the most from your data. Thank you.